Today, we'll be discussing something about the elements, about the classification of elements. Classifying elements is very essential in chemistry because it provides a structured framework for understanding the relationship between different elements and properties. This organization aids in predicting chemical behavior, facilitating research and enhancing the learning processes in chemistry, ultimately leading to advancement in various scientific fields. There is a big significance of classifying the elements, the organized elements by properties. The classification of elements provides a systematic way to organize them according to their chemical and physical properties, allowing scientists to easily identify patterns and relationship between different elements. By understanding the classification of elements, a chemist can predict how an element will behave in a chemical reaction, which is crucial for developing new materials and understanding chemical processes. Classification helps in categorizing elements into groups and periods, making it easy to study their reactions and interactions, thus contributing to this advancement in fields like material chemistry and biochemistry. Let me discuss a brief history of development of periodic table. Since ages, the scientists have been exploring various elements and somehow they got an idea of classifying them according to their properties. The classification started by Mendeleev, who published the first periodic table by organizing elements by, by arranging them according to the increasing atomic mass and thereby predicting properties of several undiscovered elements. So, the task by Mendeleev was very prominent. The idea he introduced of classifying the elements and grouping them into various groups is really a big innovation in chemistry. Henry Moseley redefined the periodic laws by establishing atomic number as the basis for arranging the elements. Mendeleev table was based on arranging the elements according to their increasing atomic masses. But Moseley did some improvements and selected atomic number as the basis for arranging the elements and thereby predicting the properties of undiscovered elements. But still, there were some flaws in the periodic table. The discovery, for example, the discovery of transuranic elements marks a significant advancement in nuclear chemistry, expanding the periodic table beyond uranium. So, according to modern periodic law, which states that properties of elements are periodic function of their atomic numbers rather than their atomic masses, as was predicted by Mendeleev. Mendeleev had considered atomic masses as the basis for arranging the elements in the periodic table. The modern periodic table underscores the systematic arrangements of elements in the periodic table, allowing the prediction of element property based on their position in the periodic table. The periodic table organizes elements systematically according to their increasing atomic numbers, thereby reflecting their electronic configurations and chemical behavior. Elements are classified into groups and periods. Groups are arranged in a column, whereas periods are arranged in a row. This arrangement allows the chemists to predict the properties and relationship of elements very effectively. The periodic trends in the properties of elements vary according to the period and according to the groups. For example, if we look at the property atomic radii generally decrease across the period from left to right because of increased nuclear charge, pulling electron closer to the nucleus. Conversely, the atomic radii decreases down a group as additional electron, sorry, the atomic radii increases down a group as additional electron shells are added. We thus come to a conclusion that from left to right, there is a decrease in atomic radii, whereas from top to down, there is an increase in the atomic radii. The ionic radii vary based on the charges of the ion. Cations are generally smaller than the parent atom because of the loss of electron, while anions are generally larger because of the gain of electron. Trends follow the similar pattern of atomic radii within the group and the period. That is, ionic radii, the size decreases as we move from left to right, whereas the size of ionic radii increases from top to bottom. The ionization enthalpy is the energy required to remove an electron from an atom. The ionization enthalpy increases across a period because of higher effective nuclear charge, and it decreases from top to bottom because the outer electrons are farther from the nucleus and thus are less tightly held, thereby need lesser amount of energy to eject an electron from the outermost shell. The electron gain enthalpy referred to the energy change when when an electron is added to the neutral atom. That is, it refers to the energy change because of the formation of during the formation of a negative ion. It is typically more negative for elements on the right side of the periodic table, indicating a greater tendency to gain electron, while it becomes a less negative as we move down the group. Electronegativity is a measure of an atom's ability to attract electron in a bond. It generally increases across a period and it decreases down a group, with noticeable exception in case of noble gases, which have low electronegativity because of their stable electronic configuration. The valency refers to the combining capacity of an element. It is determined by the number of electrons that an atom can gain, lose, or share in a chemical bond, with trends in the valency reflecting the group number for the main group elements. So far, we have discussed some of the properties and their changing trend across a group and across a period. The atomic radii refer to the size of neutral atom, which varies significantly across the periodic table. Generally, atomic radii decrease from left to right across a period because of the increasing positive charge on the nucleus that pulls the electron closer. Conversely, atomic radii increase down a group because an additional electron shell is added to the leading to a larger distance between nucleus and the outermost electron. Likewise, ionic radii are the sizes of ions and differ from atomic radii because of the gain or loss of electrons. Cations, being positively charged, are typically smaller than the parent atom because they lose one or more outer shell electrons, resulting in a reduced electron electron repulsion and greater effective nuclear charge on the remaining electrons. Whereas anions, which are negatively charged ions, are larger than the parent atom due to addition of one or more electrons, which increase the electron electron repulsion. Inert gases are also known as noble gases. They exhibit a distinct radii that exceed those of their atomic counterparts. This increase is attributed to their full valence electron shells, which create a stable electronic configuration, resulting in larger atomic size compared to other elements in the same period. The ionization enthalpy shows a distinct trend across the period and the group, increasing with atomic number in a period and decreasing down a group. For example, the first ionization energy, that is, energy of helium, is highest amongst all the elements. Its value is 10 electron volt. The first ionization energy of lithium is 5.14 electron volt. It shows an increase across the period. The first ionization energy of the element cesium is 1.03, showing that there is a decrease in ionization enthalpy down the group. The second ionization energy of magnesium is significantly higher than the first. The first ionization energy of nitrogen, illustrating the trends in non-metals, is 7.73 electron. Electron gains enthalpy varying significantly across different groups, reflecting the tendency of element to acquire electrons. For example, group 1 element have the neutron 1.3 electron. Group 17 element have electron enthalpy in the range minus 3.0 electron, whereas group 14 elements have the electron enthalpy value as zero point 0.5 electron. The noble gases have electron enthalpy equal to 0 electron. Group 16 elements have the electron enthalpy in the range minus 2.0 electron volt. The electronegativity and the valencies. The electronegativity increases across a period from left to right because of increasing nuclear charge, while it decreases down a group because of increased distance from the nucleus and additional electron cheating. This trend influences how elements bond with one another, as more electronegative elements tend to attract more electrons more strongly. Understanding the valency. Valency is the ability of an atom to bond with other atoms. It is determined by the number of electrons in the outermost shell that can be gained, lost, or shared. It is crucial in predicting the chemical behavior of elements and their ability to form molecules and compounds. Elements with similar valency often group together in the periodic table. Now, about the nomenclature of elements with atomic number greater than 100. Elements are named according to specific IUPAC guidelines, which include using a combination of Latin or Greek roots for numbers along with suffixes. This systematic approach ensures that each element has a unique and recognizable name reflecting its atomic number and other characteristics. Finally, to conclude, the classification of elements and the understanding of periodic trends are essential for predicting chemical behavior and interaction. By organizing elements according to their properties, the modern periodic table serves as a critical tool in chemistry, aiding in the study of elements with atomic number greater than 100 and their nomenclature. In the upcoming lectures, we will discuss about some other properties of elements and how the electronic configurations of various elements is done, and we will explore the class the different trends in periodic properties and the significance of periodic table in assigning the periodic properties of different elements.